We're going to be introducing a brand new concept to you guys, but I got great news for you. It's totally based off of something that we've already done. So we're going to do two-column proofs. Do any of you have parents or aunts or uncles or older siblings or older cousins that when they found out you were in geometry, they complained about having to do proofs? Anybody ever heard that from someone? So I have taught geometry for a long time, and my students, the biggest complaint that they always had was with proofs. And the reason was, I think, is most of the time, most textbooks, when you're learning proofs, you learn it like way back at the beginning of the year. And they don't teach, most textbooks don't teach a flowchart proof. They teach these two-column proofs straight from the beginning. What I've found since I've been teaching out of this book for the last 2 years is that it's way smarter to do it this way, because flowchart proofs, if we start them late enough, we've been dealing with the idea of like evidence for stuff all year. So we've already got that idea. You guys understand how that works. I'd say most of us in here are starting to get pretty confident with putting together a flowchart, maybe with a little bit of help. Going from a flowchart proof to a two-column proof is really easy. I'm going to show you today. So if you're feeling confident with flowchart proofs, then what I'm going to show you today is going to be like, no problem. Okay, if you're still struggling a little bit with flowchart proofs, that's okay. Probably I would expect that most of us aren't 100% of the way there yet. But you'll still be able to do this. Okay, so our ultimate goal for today is, if I have a flowchart proof in front of me, can I turn it into a two-column proof? So we're going to start with a problem from 7.2.5. And if you want to open up your book, you can. You don't have to, because I'm going to give you everything you need up here. All right, so we're going to actually start with number 91. And I'm going to draw the picture that's in the book here. I'm going to rotate it a little bit. They've got theirs at a jaunty little angle. I'm going to put mine at a not so angle. It's got a right angle in it. And this is M, this is B. Oop, I forgot something important. Tick mark, tick mark. And they called this line L. All right, we've got some important vocab that I want to make sure that we've got before we get into the actual proof here. This line L, has a special name. It is called a perpendicular bisector. Perpendicular bisector. It's a pretty official sounding name. You getting this in your notes? We all know what perpendicular means. We dealt with it a bunch back in first semester. Remind me though, what kind of angles do you have to have for something to be perpendicular? 90-degree angles, right angles. Do you see some right angles in the picture? So this is perpendicular to AB, to segment AB. So perpendicular means that you've got right angles or 90-degree angles. And bisectors come up a couple times recently. In fact, on Wednesday, we dealt with bisectors. Bisector, remember, take that word apart. Bi means two. Sect means what again? What do you do when you dissect something? You cut it, right? You cut it up, take it apart. So bisect means cut into two. So cut into, and not just two, but two equal parts. So do you see how that line L, that one that's going vertically, do you see how it is cutting that other segment into two equal parts? And we know that those parts are equal because of those tick marks here. So this is a perpendicular bisector. It is cutting it into two equal parts. So there's this theorem that says, and this becomes pretty useful in a lot of applications, especially for like architecture and that kind of stuff, planning, city planning. Anyways, the theorem says that I can take a point, this point P here, and I can slide it anywhere I want on that perpendicular bisector, and that point P is always going to end up being the same distance away from A as it is from B. Okay, let me say that again. I can take this P and I can put it wherever I want on this line. I could put it here, I could put it down here, I could put it way up here. As long as it's on this perpendicular bisector, it will always remain the same distance away from A as it is from B. Do you believe that? Does that make sense to you? So if you imagine this P is kind of being a rail and we're sliding this thing up and down the rail, it's always going to end up being the same distance away. If I moved it down to here, those distances would still be the same. They'd be smaller, but the distances are always going to be the same as each other. All right, so that's the theorem that we're going to try and prove. And we're going to do it two different ways. So I'm going to start my flowchart proof kind of underneath here, and I'm going to save some space next to it because after I make the flowchart proof, then we're going to translate our flowchart proof into a two-column proof, the new thing that we're learning today. So I'm just zooming out a little bit so I can see this. Let me see if I can get rid of this menu and give myself some more space up here. There we go. All right, so we're going to want to start with some given information. What we ultimately want to prove is that no matter where P is, we want to prove that PA is congruent to PB. If I could prove that, then I will have proved to you beyond a shadow of a doubt that no matter where I put P, it's always going to be the same distance from A as it is from B. All right, now we've been practicing with congruent triangle proofs. Do you see some triangles we might be able to prove congruent here? Yes. Do you see anything that we could mark in this picture that's not marked currently? The two sides, you want to mark these ones? I would love to, but we can't yet. That's what we're trying to prove. Once we get finished with our proof, we will be able to mark these two sides, but I can't mark them just yet. That's what we're trying to prove. So we can't use the thing that we're trying to do as evidence for itself. That would be a circular argument. But what else could I mark in here? The right angle, there's another right angle here. That's awesome. Hey, so I've got a pair of angles in my two triangles. I've got a pair of sides from the given information. What else can we mark? Line L, yeah, this shared side in between, right? Remind me of what we're going to use for our reason in our proof. Reflexive property, good. Okay. So we're going to start with a bubble. We know, oh, before we move on, what reason do you think we're going to use for our two triangles being congruent? SSS, AAS, ASA, SAS, HL, what do you think? SAS, we think that we're going to probably end up using SAS. I'm just going to make a note of that. Okay, yeah, because I got two sides, this side, and these angles totally. So I'm going to start off with this. Line L is a perpendicular bisector of AB. That's going to be my first bubble. And that's going to be my given. That says line L is a perpendicular bisector of AB. All right, so if line L is a perpendicular bisector, that's the thing that told us that these two pieces would be equal here. So I'm going to have a bubble coming off of here that says that AM, that's this piece of AB, is congruent to MB. You looking for a pen? I got pens. I don't have any pens. Oh, you got it. Okay, now technically this was marked at the beginning of the problem. I could use given for this, but I'm going to base it off of the fact that they told us it was a perpendicular bisector. So my reason for this is not going to be given. It's going to be definition of a perpendicular bisector. I'm abbreviating bisector BIS. Take a minute, look that over, make sure you got it copied down, and see if you can figure out why I have those two things going into each other. If line L is a perpendicular bisector, do you see how that forces these two sides to be equal? They have to be. Bisect means it cuts it into two equal parts, right? So if I tell you line L is a perpendicular bisector, then there have to be two equal parts here. What's the other thing that a perpendicular bisector tells you? Not just that we're cut into two equal parts, but what else? What's the perpendicular part tell you? Someone help me out here. Come on, guys. I know it's Friday and it's rainy and gloomy outside. Perpendicular means what? You got it in your notes. We got it in your notes. Right angles. That means right angles, right? 90-degree angles. Okay. So we're going to put that also coming off this to another bubble. Okay. So we've got two right angles and we need to name them. We can't call them angle M. So we're going to have to go 3 letters here. No. Have a seat. I need you to wait for the pass to come back. So I got AMP is equal to angle PMB is equal to 90 degrees. They're both equal to 90, which means they're equal to each other, obviously. And my reason for that is going to be definition of perpendicular bisectors again. So what I'm doing is I'm building up evidence for our SAS. I've got the sides, I've got a pair of angles. I need another S. What's the S that I'm missing? What's the set of sides that are equal to each other that I don't have in my proof yet? We marked it in our picture, but it's not in our proof yet. Max, what are we missing here? So to do SAS, I need a pair of sides, a pair of angles, and another pair of sides. I got a pair of sides here. I did AM and MB. That was weird. What just happened? Power outage? Yeah. Power flicker? You turned it off. Why did you do that? I need you to stay. Four minutes. You got 4 minutes. Okay, go ahead. No, you can go. I need you back in 4 minutes. What am I missing? What am I missing? We're missing the reflexive property here. Let's stick another one. I'm trying to save space here, so I'm going to squeeze my reflexive property in here. You still can't see, sorry. I'm going to squeeze my reflexive property underneath that long bubble that we just did. Hopefully we're coming back here. PM congruent to PM. Reflexive property. Sorry about the technical glitches, folks. Hey, stick with me here, please. You guys get that bubble in there? Do we have enough information for our triangles now? Yep. We've got our side, we got an angle, we got sides. So let's do our two triangles congruent. We've got evidence that's going to lead us to this. Let's see, we got triangle. I'm going to call this one APM. And I'll call the other one BPM. Is that what we were trying to prove, or is that just a step along the way? That's just a step along the way. We were trying to prove, we took some notes up here, and I apologize that I can't show this all at once. Maybe if I tilt my paper. We were trying to prove that PA was congruent to PB. Do we have enough information to prove that now? Yes, because why? Oh, I forgot my reason here, SAS. The triangles are congruent, right? If the triangles are congruent, all of their parts have to be congruent also. You have now proven to me that these two triangles are congruent. That means that these angles match. That means that these angles are the same. That means that these sides are the same. And that's what we were trying to prove. So you had suggested that we mark these at the beginning. We can mark them now, right? Because now I know for sure they're congruent. But let's go ahead and put it in our proof. So our final bubble is going to come off of this. Now that I know the triangles are congruent, that leads me to the conclusion that those two sides are also congruent. So we've proven this theorem, big famous theorem called the perpendicular bisector theorem. It's in almost every geometry textbook ever written. Our reason here, do y'all remember the reason that we use when we're coming off of a triangle bubble? Congruent triangles lead to congruent parts. Okay, we've now spent 3 class periods reviewing this, okay? This needs to start becoming second nature. I proved the triangle's congruent. I got a bubble coming off of that. My reason is congruent triangles leads to congruent parts. Okay, if you're not able to recall this quickly, then you need to spend some time studying that. All right, now that's all review. We've done all that stuff before. Here's the new thing I'm going to show you today, and it's called a 2-column proof. Sorry, move it down a little bit. 2-column proof. We're going to do our first 2-column proof. As you might suspect, it is going to have exactly 2 columns. On the left, we're going to have statements. And on the right, we're going to have reasons. Now, I'll give you the cheat code here. The statements are going to come from the inside of bubbles. Talking about our flowchart proof. And the reasons are going to come from the outside. So for each of these bubbles in my flowchart proof, I'm going to have a line in my 2-column proof. And all I have to do is copy the inside of the bubble in this column and the outside of the bubble in this column, and I got to get them in the right order. So the only tricky thing about this, and I'm going to use air quotes around tricky because I don't think it really is that tricky. The only tricky thing about this is you got to get it in the right order. And here's the rule on that. If you've got 2 bubbles and one is flowing into the other one, then the evidence has to come before the conclusion. So I don't know which step of my proof this bubble is going to be, but I can tell you for a fact it must come after this one. This one has to come before it because this one provides evidence for this one. You get what I'm saying? This one right here, do you see this bubble right here? You see how there's nothing leading into it? It can go anywhere in the proof I want to, as long as it comes before this one. It's got to come before this because it leads into that one. Okay, so there are lots of different orders that are correct. The key thing is that if something is evidence, it's got to come before. So typically, when you're doing this, you end up starting at the top because this is the stuff that started everything, and you work your way to the bottom. I can tell you for a fact that there is one statement that has to go in a particular spot. I can tell you what the last statement of my proof is going to be. What's the last statement going to be in my proof? I just saw a couple of people mouth it, and you're totally right. This has got to be the last one, right? Because everything flows into this. This can't come before anything else because everything else is evidence that leads up to this. So here's how we're going to do it. We're just going to write number 1, and we're going to pick some place to start. I could start with this one because this doesn't have any evidence going into it, or I could start with this one because it also doesn't have any evidence going into it. You guys want to just start up at the top? Let's do it. Line L is a perpendicular bisector of AB. We write a little 1 next to it to show that's our first line. And then over in our reasons column, we'll also put a 1 and we'll put our reason for it. And the reason we had outside our bubble is just given. Where do we want to go next? I'll show you a little trick here. You guys want to see a little shortcut cheat code here? You see how these two bubbles have the same reason? We can squeeze them into the same line. If they have the same reason, we can put them in the same line. So I'm going to go ahead and do number 2 as AM congruent to MB and angle AMP is congruent to angle PMB. I'm squeezing both of those bubbles into the same step, and I'm allowed to do that anytime the reason is the same for both of them. And the reason for both of them was definition of a perpendicular bisector. Now, I didn't have to do that. I could have had that be line 2 and line 3, and I could have just repeated definition of angle or perpendicular bisector a couple times. But you are allowed to squeeze multiple reasons into the same step in a 2-column proof as long as you're allowed to squeeze multiple statements into a single step as long as the reason for both statements is the same. What do we want to do next? We could do the triangles next, or we could do this next. Actually, I don't think both of those are an option. Can I do the triangles next? Do the triangles rely on something that we have not put in our proof yet? They do. They rely on this also. So this has got to come before the triangles. We've already got these 2 in our proof, but this one needs to come before the triangles because the triangles rely on that. So step 3 is going to be PM, PM. By reflexive property. And then step 4, we could do the triangles. And then triangle or step 5 is going to be our conclusion. It's got to be the last one. It's the only thing we're missing right now. All right. And that's it. That's 2-column proofs. So if you can make a flowchart proof, you can directly translate it into a 2-column proof. The only tricky thing about it is making sure things end up in the right order. So if something needs some evidence, if we need this, these triangles needed 3 pieces of evidence, these 3 pieces of evidence have to come before this step in my proof. That's it. We got to think about it like a court case, right? If I'm going to present evidence in a court case, I need to present it in an order that's going to make sense. I can't present this evidence and then go back and talk about the things that support it afterwards. We need to present the support first. So my big question for you, and we'll do this on our thumb meters. If I were to give you a flowchart proof, how confident do you feel putting it into a 2-column proof right now? Show me on your thumb meter. You're like, yeah, well, that looks easy. I could do that. Or we've only done 1 so far, so I think I'd want some more practice. Or I have no idea what a 2-column proof is. Where are we at? Awesome. So we're in the learning zone. I'm seeing most people are saying we've only done 1. So why don't we do another one and see if we can move those meters up? Okay. Question before we go. Yes. Oh, okay. You know what? I'll bring it over to you. Does anybody else need a minute? So here's what I'm going to do. I'm going to ask you to go back to our first proof from Wednesday. If you were not here on Wednesday, you are in luck because I've got it. I'll put it up on the screen here. Go. Yep. That's not it. There it is. This is the first proof that we did on Wednesday. You should have something in your notes that looks similar to that. It's going to look maybe a little bit different. And here's what I want you to do before you start on your assignment today. I would like you to turn that flowchart proof into a 2-column proof. And then I'd like you to get my attention. Let me look it over and make sure everything's in the right order. And then you can begin on your assignment, which will be the next one on the assignment sheet. If you don't have this in your notes, I want you to put this into your notes. So if you weren't here on Wednesday, or if you weren't taking notes on Wednesday, the flowchart proof needs to go into your notes as well. If you already have a flowchart proof in your notes, that's fine. Find another spot to go ahead and put your 2-column proof in. Yes. Auxiliary line. So when we got this picture, it did not have this line down the center. So we drew that line in. So you're allowed to add lines into a picture. And we drew it in specifically so that it would bisect this angle up here. So it would cut it into these 2 equal pieces. So what we learned, what we started with was there was just a triangle. And our goal was to prove that these 2 angles were congruent. Well, we already had these sides here. And what we decided to do was if I were to draw a line in here that actually cut this angle into 2 equal pieces, then with my reflexive property, I'd have enough to do SAS there. Does that make sense? So you're allowed to actually add additional things into it. When you add something that wasn't in the original picture, we call that an auxiliary line. And you need to describe exactly how you're doing it. We decided to do it so that it would cut those angles so that we could do SAS. Another class actually did it a different way. They decided when they did their auxiliary, so it was like this. They decided when they did their auxiliary line to cut it so that it was a bisector for this, which meant this was equal to this. And then with your reflexive property, you get side, side, side. Okay, so theirs look different. They said BD bisects AC. Instead of bisecting the angle, they chose for it to bisect the bottom. And then this would be definition of a bisector also, but except theirs said AD is congruent to DC here, and this was SSS. So does that answer your question? Yep, thanks for asking about that. That's the first time we've seen that, so I'm glad you asked about that. Okay, everybody understand your task right now? Some of you are probably halfway done by now. You're gonna just translate this into a 2-column proof. You're gonna get my attention. And once you're done with that, and I've confirmed that you got it, then move on to your assignments.